Back, everybody. It is my absolute pleasure to introduce our next speaker, Andrei Gabrielov, who will tell us about Lipschitz geometry and the combinatorics of abnormal surface germs.
Thank you very much. And I should apologize that this topic is not exactly in Frank Satil's environment, although I did work on many related problems with Frank and on Frank's problems and things like this. But for some reason, I moved to a different area. Lever-Breyer was the origin of that. And this is a joint work with Emmanuel Souza, who was a graduate student from Brazil, and he spent a year at Purdue, where we did work on this paper. So the goal is the classification. It's actually singularity theory for semi-algebraic or more general definable in polynomially bounded or minimal structure sets, real semi-algebraic. And everybody knows that in algebraic geometry, real algebraic geometry and complex algebraic geometry, you can classify things by algebraic or analytic way, and that immediately gives you very complicated moduli, or you can do it topologically, and that's discrete but really too rough. So the Lipschitz classification is something in between. There are theorems about absence of moduli in Lipschitz classification, but first of all, there are several kinds of Lipschitz classification. So let me start with the definition of what we have here. So you can think of a real semi-algebraic set, and it is in the Euclidean space and inherits two metrics. The outer metric is just the distance in the ambient Euclidean space. The inner metric is the shortest path between 2 points inside our subset X. And there are and there is an important notion of things being normally embedded. Let's see how that looks like. Oh, okay, I don't know where the point is. So the thing is normally embedded if these two metrics are equivalent. So and then you can classify such sets up to the inner metric is always longer than the outer metric, and you can classify to the inner metric, and that was done by Lever-Breyer in '99, quite a long time ago. And then immediately the natural question was, what about outer metric? So the problem is still open, but we are pretty close, I believe, to solve it with Lev. But it happened that the problem is much harder. So the important part is the finiteness. So there are several theorems in different generality that essentially all say that in any classification, there is actually ambient classification of such sets, which means that you need not only map one set to another, but also to map the ambient space to another space in bi-Lipschitz way, which is even more sophisticated. In fact, like in the four-dimensional space, it involves all the not theory and more. But I'm not going to talk about ambient today. So the inner classification is more or less easy. Essentially, you just take singular arcs in your set and look at the connecting two-dimensional pieces. Yes, and everything that I'm going to do today is about a germ at the origin of a real two-dimensional semi-algebraic or definable set. And so let me move over. So what are the building blocks? The analog of a simplex in this area is called the standard Bethe-Helder triangle. Just it's a triangle. In fact, it's a germ bounded by two arcs, and the tangency order within the arcs is beta. And another important object is called standard beta horn. So it's the link is topologically a circle, but the exponent, you can think of the exponent as you look at dynamics of the link. The link is the intersection of the sphere of radius epsilon. Epsilon goes to 0. How the link behaves metrically. So metrically it contracts with the exponent beta, and that would be a beta horn. And in most pictures in this talk, the two-dimensional objects will be represented by their one-dimensional links and just pointing to the exponent. So these are building blocks, and essentially in inner classification, all you need is these two things, and everything else is combined out of them. But in the outer metric, as I mentioned, that in inner metric, essentially you can choose the singular arcs, and all the classification is there. Like there is a graph. A link is a graph with the vertices singular arcs and edges the Helder triangles connecting them. In outer classification, the problem is that it's really hard to find an arc in your two-dimensional set not to introduce some kind of an extra exponent that should not be there. So the geometry of the set itself is pretty tricky. Again, other than singular arcs, you cannot find anything which is invariant, outer Lipschitz invariant. So instead, what we are going to do is to replace our two-dimensional germ by an infinite-dimensional set of arcs in this germ, which is called Valette link, following Guillaume Valette. And it is the space of all arcs. Again, an arc for us is a one-dimensional germ in our two-dimensional or high-dimensional set, parameterized by the distance to the origin. So you can think of it as a mapping of an interval to our set, or just as a subset of our set, and that's what we usually do. Think of an arc as a subset of a one-dimensional subset of our set. So this Valette link has a metric defined by the tangency order. If you have two arcs, you can think of how the tangent at the origin, there is an exponent, kappa, well, for semi-algebraic set, it's a rational number. In general, it belongs to some kind to an exponent field. And the result is a non-Archimedean metric. You can take 1 over tangency order, or if e to the negative tangency order. Well, there are many ways to define, but the key point is that it's an infinite dimensional space with a non-Archimedean metric, and that's where we are working. So the advantage to work in this space is that there are a lot of outer Lipschitz invariant subsets. Unlike our original set X, there are lots of outer Lipschitz invariant subsets in this valid link. So there are singular arcs, and actually there are Lipschitz singular arc with respect to the outer Lipschitz metric, which are maybe topologically non-singular. Like you have a corner, and when you go to the origin, the angle goes to 0. That would be a Lipschitz non-singular link with the Lipschitz singular arc. And again, there are finitely many of them, which is good. And that's the only thing that we can really choose as outer Lipschitz invariant in our sets below. And our building block, again, is a Hölder triangle, which is, again, something equivalent, by Lipschitz equivalent to the standard Hölder triangle. It has one exponent, beta, and it is, all our Hölder triangles should be non-singular. That means we allow a singular arc at the boundary, but not inside. And the final is, if you have a beta Hölder triangle, then the arcs which have beta tangency with its boundary arcs are called generic. So now we want to identify certain structures inside of our space of arcs, and important notion is a zone, which is an analog of an interval in the space with non-Archimedean metric. So it's formally definition is that it's a set of arcs such that for any two arcs there is a Hölder triangle such that those two arcs are boundary arcs of this triangle, and all other arcs belong to our set Z. So it's a replacement of connected interval for the non-Archimedean metric. And so the zone has an order, which is the minimal tangency order of arcs in it. And we also have this notion of normally embedded zone. Again, normally embedded means that its inner distance is equivalent to its outer distance. And, and there are closed and open zones. Well, again, because of this peculiar non-Archimedean metric, this exponent beta may be infimum or supremum or minimum of all exponents. If you have two arcs in this zone Z, so you're looking at the minimal value of exponent, so that the arcs are further away from each other, and for some zones, its minimal value indeed is achieved. There is a couple of arcs with this beta tangency, and that we call the zone closed. If it is not achieved, it's infimum, then it's open. And then really good zones are called perfect. A perfect zone is such a zone, so if you have any two arcs in this zone, you can find a Helder triangle such that all arcs in this Helder triangle belong to our zone. So V of T is the Waliot link of T, which means all arcs in T, such that both of our arcs are generic arcs. Essentially, if you can think of perfect zone that you can move things in by Lipschitz way in this zone, and any arc you can move to the other any arc just by Lipschitz transformation of the whole zone. So that's why it's so good. And all these properties are, again, outer Lipschitz invariant, so we can use them. Again, we have this notion of normal and abnormal, so let's start with an arc. So we start with a non-singular, Lipschitz non-singular arc. Lipschitz singular arcs are finitely many, so we already know where they are, we don't care about them. We want to deal with the non-singular arcs. So, and non-singular arc is called abnormal if there are two normally embedded Helder triangles such that the intersection is exactly this arc, and the union is not normally embedded. Otherwise, an arc is normal. And accordingly, a zone is abnormal if all arcs are abnormal. A zone is normal if all arcs are normal. And there is a finiteness property. So given a germ X, just look at all abnormal arcs. There are finitely many zones, so those abnormal arcs constituted finitely many zones inside this Waliot link. And also, all normal arcs constituted finitely many maximal normal zones. So, moreover, all maximal abnormal zones are closed perfect. And there is a notion of weakly normally embedded. It's not all exactly normally embedded, but there is some, again, nice property. Okay, and here we come to snakes. That's the main object of our paper. So a beta snake is a non-singular beta Helder triangle T such that the set of all abnormal arcs in T is the same as the set of all generic arcs. So, like here is an example. So in green, there are, I already mentioned that what this example means, it's a link of a germ of a two-dimensional surface. So it's really hard to draw a germ of a surface, but it's easy to draw a link, which is one-dimensional. And to identify what is going on with exponents, we actually put here is the beta, and here is beta. And this gray area means that this tangency order is higher than beta. So our snake has the places where it like hits itself. So this part is contact higher than beta. This part is contact higher than beta. And again, on this plot, you see what why this arc is abnormal. Because there is a normally embedded triangle, this one, and there is another normally embedded triangle, this one, but the union is not normally embedded. The outer distance here is higher than, so the whole thing is beta, has exponent beta, but the exponent here is higher than beta. So the union is not, the two metrics are not equivalent. And so all the red part is abnormal. And only at the end of this segment, there are green parts which are normal, and there are really few. This is an open zone. So whenever you have exponent beta with this boundary arc, you already are here in red. There is also a circular snake. A circular snake which has like no head and no tail, but all of its arc are abnormal. So again, in this plot, you can see that everything is red. Each arc here would be abnormal. Okay. Finally, there are non-snake abnormal zone, and this is a bubble snake. This is still a snake. So this again a beta zone, but a very simple snake, which is called a bubble. You understand why, and it has some unusual properties. In a certain sense, it's the simplest possible snake, and all other snakes can be produced growing out of this. And there are different kinds of non-snake bubbles. So non-snake means you have, like, this is the simplest thing. You have like a cucumber with a top. So, and if you look at the property being abnormal, the only this beta part in red on the top is abnormal, but the sides are too long, and anywhere beyond beta from the top, you get normal arcs. So they're non-snake because there is no snake that contains such a zone. And that's essentially everything about abnormal zones. So the theorem is that for any surface germ, each maximal abnormal zone is either a beta snake zone, or a circular beta snake zone, or a non-snake abnormal beta zone. And again, the important zones are perfect, like non-snake abnormal zones are closed, perfect, and each maximal beta snake zone it consists of a segment where nothing happens and nodes where the snake hits itself. And the nodes are also perfect zones, but they're open perfect. And segments are closed perfect. So the result that actually all abnormal parts, first of all, this is a canonical decomposition of the Wallet link, canonical in terms of the outer Lipschitz equivalence. You have Lipschitz transformation of one set to another, then all those zones map to the corresponding zones between. So all those zones are outer Lipschitz invariant. And that's why we need this, because we need something outer Lipschitz invariant to do outer Lipschitz classification. So that's how it looks like. So here's our snake. So there are nodal zones in red here. In black is some segment zone. And at the end, in fact, there are some other zones where you could put this boundary arc here, or you can put here, or a little bit further. It will be still a snake. So there are some kind of these are normal arcs that are green, but they play the same role as the nodal zones. So they are just the result of our snake. Our snake may be part of something, and we just cut it there to make it a snake. So the idea is that some part of snakes are nice and have this exponent beta with all these relatively bad parts, and so some parts are where really snakes hits itself, and these are also perfect zones, and they're called nodal zones. And here we come to combinatorics. So we have a snake. So let's go back to snake. Oops. No, that's not exactly. Okay. So if you have a snake like this, you can start at the end, assign some letter to this node, then you get to another node, assign another letter, then you come back and you get the same letter here, and so on. As a result, you get a word which is called the snake name. So formally, a word is a snake name if each letter appears at least twice. So we need, if you have a nodal zone, there should be at least 2 pieces of snake that hit each there. And there is another condition is that we want our snake to be abnormal, and that means we have to go from each place and come back somewhere else. And combinatorically, it means that for any k, so for any place in this word W, there is a subword where the initial and the terminal letters are the same, and there are no other repeated letters. So, and in terms of geometry, means that our WK corresponds to an arc in our snake, or a zone actually, and take an arc in this zone, then we know that there are Hölder triangles with the abnormal union and boundary in this arc. And that's exactly the 2 minimal such Hölder triangles would give you this WJ and WL, which belong to the same node, and that makes them not normally embedded. So there is some kind of maybe combinatorially strange, but geometrically very natural condition on this word, which is a snake name. Well, here is an example. So you have A, B, C, D, A, C, B, D is a snake name. You can see that the first, the ends are not, do not matter. You cannot have, like B, C, and D are between 2 A's. Then A is between 2B or between 2C, and or between 2D, and so on. So, so this is a snake name, and ABA, CD, CBD, is not a snake name, because if you take the second entry of A, so ABA, if you go to the left, you only can get B, and you go to the right, another B, but between this B and the other B, there are two C. And that's forbidden in the definition of snake. So there is some combinatorial condition that gives you a set of words, and in fact, to each snake, we assume snake to be oriented, so you know where its head and where its tail. You can assign this word naturally, and other way around, given a word, there is a snake with some with this word. So the number of distinct letters is the number of nodes in the snake, and the length in the total number of nodal zones. So this is the simplest, a bubble, which has name AA. The next simplest is ABAB, and this one is ABABA. There are only two nodal zones, but one of them is triple, and that's why there are only two letters, A and B. But the number, the number of nodal zones in the snakes, because one of them is triple, then you have 2 plus 3. There are 5 places where the snake hits itself, and that's why the length of the word is. Now, what we want to do is to count our snakes, and unfortunately, to count arbitrary snakes happen to be hard, so we try to do some simpler snakes, which we call binary. So a binary is if there are no triple nodes like this. In particular, if you have any snake which is not binary, it's a non-generic. So like we have a triple node like this, we can shift these two pieces, like shift A into 2A and A prime, and then we'll get a binary snake. So a binary snake is essentially a generic kind of snake that triple is not generic. So there is a canonical way actually to reduce every snake to a binary snake. And essentially, because we don't know how to count general snakes, let's count binary snakes only. Okay. For binary snakes, there is a recursion. The recursion is the following. Given a binary snake, you can increase the number of letters by adding an extra node in it. And there are two ways to add this extra node. Well, of course, to add an extra node, you need to do it twice, because every letter appears twice in binary snake. So, and there are two different ways. You can put an extra node in the beginning of the snake, or one in the beginning and one further away. What means further away? Snake has the first letter of snake, let's call it A. appears again somewhere in the snake. And then there is essential difference between the interval between the first letter and the second entry of the first letter and everything beyond. So these are two different ways to extend our snakes to have an extra letter in the beginning or not in the beginning, and that gives you a recursion in the number of snakes. And yeah, and the statement is that starting with a simple bubble, the snake with the name AA, and using these kind of two operations, you can obtain uniquely any binary snake. So that's how we can count binary snakes. There are, unfortunately, recursion is two-parametric because of the two kinds of ways you can insert extra letters. And there is a formula but for recursion, but I have no idea how to make it an explicit number. So it's an open problem. Is there an explicit formula for those numbers? I don't know. But, well, because I don't know, I'll try to find inside this set of binary snakes something that I can handle. And this is a way to assign a standard Young tableau to a binary snake name. So it's well, first of all, since it's a binary snake, it has each letter appears exactly twice. So the Young tableau is with two rows of length m, which note that our snake has 2m plus 2. So it's not like we just have our snake put on the first row and half our snake is the second row. We essentially have to remove the boundary arcs. Our snake has boundary arcs, and our word has the first letter and the last letter. We have to remove them and put the last in the letter. So we start with the second letter, I equals 2, and insert I minus 1 in the first row if this is the first entry of the letter, and then the second row if it's the second entry of the same letter. And there is an easy argument. Then this way we get a standard Young tableau with the shape 2 by m. So it's one column shorter than would be the length of the snake. And so there is, and moreover, for each standard Young tableau, well, I explained why it is a Young tableau, but that is standard. It actually follows from the conditions on the snake name. It's not obvious, but it happens always to be standard. And other way around, if you have a standard Young tableau, there is a canonical way to recover the snake name. And now, again, I don't know how to count all binary snakes. There are many binary snakes that give you the same Young tableau. And in fact, I don't know explicit formula for that. But now let's get a little bit simpler again. So for each standard Young tableau, there is a unique inversion-free snake name. So that means in the snake name, there is no like x, and in between y, y. So if you get x, y, then should be x, and then another y afterwards. So any two different letters cannot appear one couple inside another couple, and only like this. X first, y second, x third, y fourth.
I call that non-crossing.
Non-crossing, yes.
Right, arcs between that.
Yes, yeah. So we assume that, yeah. So the statement is that for any such for any Young, so you can find a Young tableau for any binary snake. You can define it, and it's always a standard Young tableau. But among those snakes that give you the same standard Young tableau, there is exactly one non-crossing. And so the consequence is that the number of inversion-free or non-crossing snake names for binary snakes of length to m plus 2 is m's Catalan number. So again, there are lots of open problems here. You can see combinatorial. They have very natural geometric origin. So you start, well, at least this non-crossing binary snakes, you know how to count them. If they are non-crossing, again, I had lots of numerical experiments how many binary snakes give me the same Young tableau. I couldn't find the rule. And of course, if it's non-binary, then it is even more. Although for non-binary snakes, there is a recursion relation, two-parametric recursion relation that allows, in principle, you can just count them by doing this relation, but I have no idea what the explicit formula is. I think that's all. Happy birthday, Frank. Sorry, I didn't do about anything about Shapiro and Shapiro, but this Catalan number is something that is definitely associated for me with Frank. Yes.
I do have a question for you. So the Catalan number connection is really interesting, and I wonder if the operation from going from any snake to a binary snake would be similar to Knuth's algorithm for going from any tree to a binary tree, because those are also both counted by Catalan numbers. And moreover, since we have so many Catalan objects out in the mathematical space,
Yes.
I wonder whether finding a bijection from an inversion-free snake to one of those objects like a tree or just anything, whether understanding that bijection could give you a way of thinking about how adding an inversion might look in this other type of object to make it easier to count the.
Well, that's a good question, but well, first of all, you see, Catalan number only appears for the non-crossing
Sure.
binary trees.
So, sure. So the point that I want to make is that some Catalan objects are obtained by some large class of things like permutations, but with a pattern avoidance imposed on it. And so this might be so you have here a large class of objects with a pattern avoidance imposed upon it. And so there could be a connection to something that could actually be fruitful.
It could be, yeah, but I, I don't know.
Just a thought.
Yes, yes, and of course, well, the translation from any snake to a binary snake geometrically is very simple operation. You just have there is actually a canonical algorithm that allows you to get from any snake name to a binary snake name, and then to recover that if you know which letters get, so like you have A, which is triple letter, instead of you get A prime and A prime prime, two pairs, and then if you know those clusters, you can again canonically recover. So there are all kinds of ways and relations here which has natural geometric meaning, but I'm sure they also should have some kind of algorithmic.
I mean, combinatorics deal with objects in history who have a semi-standard version of something, and there's a standard way to make it standard for each.
Yes. Yes. So yeah, I wouldn't be surprised that just my combinatorial ignorance doesn't let me understand it.
Other questions? Great.
I don't follow the snake world that closely, but in the snake language, you have words just in a free semigroup, right? No.
No, I don't.
There are conditions. There are some conditions.
There are conditions on those words. No, I cannot just add to such words and get a snake. There is no additional operation. It would be not a snake. And again, geometrically, I'm coming from Lipschitz geometry. A snake is an interval with all arcs abnormal. So if I combine two snakes, I may get a bigger snake, or I may get a normal interval in between.
My point is not that it's a subgroup of something or subsemigroup, but there is a standard way in combinatorics to create generating functions if you know that your language, the collection of words, is regular. In other words, it could be generated by a finite automaton. So if it seems like the generation procedure here is quite well described.
Yes.
So it wouldn't be.
That's what I told. Yeah. There is an explicit two-parametric recurrence here. So the generation of all that gives you all words uniquely. Yeah. So it is automaton, but the question is whether you can also have a closed formula for this number other than just the algorithm. I have an algorithm that produces all snake names.
You can produce the closed formula for generating functions and then then the coefficients of.
It would be very interesting if you could.
Anton's point is oftentimes you have some combinatorial sequences, and it's hard to understand them, but you package them together and generate them. They satisfy fairly reasonable properties like differential equations or rational or many other.
Yes. Say if this function turns out to be something from which you can extract the coefficients explicitly, then that solves your problem.
Yes. So yeah. Okay. It's a published paper in 2022, and all those are there. So if anyone who is a better expert in combinatorics than myself can get it, I'll be happy.
Yeah, we are in the combinatorial algebraic geometry community. We need to permute the words. Algebraic combinatorics would be
Yes.
the people who will solve it.
So it's not like that this classification is very complicated. What if you have semi-algebraic set which is given by not very complicated formulas? Say, can you, for example, you know, in singularity theory, if you know that the dimension is small, you have very simple classification. Do you have anything like that? Kind of simplest, what can happen for simple semi-algebraic set?
Well, of course, there are, this is metric property, not topological property, but again, for all topological properties of semi-algebraic set, it's known that the low complexity gives you upper bound on topological property, and I'm sure that it should also give you upper bound on this metric property. And again, that's why I advertise this Lipschitz geometry. So Lipschitz geometry, essentially, everything is fine. There are no moduli in any Lipschitz geometric problem. Everything is discrete, so you can count everything. And I'm sure that for small complexity semi-algebraic sets, there also should be upper bounds on the complexity of these sets, but I never thought of this, and in fact, to understand, for example, which of those snakes can be realized by like low complexity semi-algebraic sets, it's completely out of reach.
I have a question. So these snakes with no heads and no tails, these
Yes,
Orosporos.
Yes, there are circular snakes, and actually, Emanuel Souza is currently finishing, but not exactly finished, a paper classifying circular snakes, and there is a completely different kind of recursion for them too. But in this paper of ours, we didn't do much other than the definition. The definition you only need because there is this universality theorem. So the main theorem, so actually our goal, I already mentioned, is to classify surface germs with respect to outer Lipschitz equivalence. And the classification actually is extremely non-trivial. Moreover, we have already 2 papers with Lev Beer on the following objects. So let's try to take a normally embedded Helder triangle. There is nothing simpler than a normally embedded Helder triangle from the point of view of Lipschitz geometry. Oh, I'll tell you what. So it's like a building block. It's like a simplex in triangulation. Now let's take 2 normally embedded Helder triangles. There is a complicated set of invariants that refers to the outer Lipschitz geometry of such a pair. And we have 2 papers with Lev Beer on that. And that's only the beginning, because then, of course, when you have a general surface germ, you have a lot of different pieces which interact with each other, and that's a big mess, which we didn't, well, we know a lot about it now, but it's still not everything.
Okay, thank you. Any other questions? Then let's thank Andrei again. I'll see you after lunch.